This is the model that we built in Module 7. We worked mostly on this part, building hospital capacity and calculating hospital availability, which affects the recovery rate as well as the death rate. So now, before we move on, we're gonna do two things. Make sure that you run the Module 7 base, and then also run the Module 7 with the burnout switch turned on. So by default, the burnout switch is set to 0, but if you change that to 1, then you are actually activating this burnout part of the model. Now we are ready to add the structure for quarantine policy. If you look at the model right now, the variables and arrows are in gray. That's because I want to have the new variables that we're going to be adding in this model to pop out a little bit more. So they're going to be in black. The rest of the variables from the previous modules will show up in gray. Okay, as you can see, our model is becoming quite complicated. Okay, so the first part that we're gonna do is how the death rate will affect the quarantine policy. So just like the effect of death rate on number of contacts and effect of death rate on infectivity, we're gonna create a variable here. It's gonna be called effect of death rate on quarantine policy. And then I'm going to say this is pressure to quarantine. Okay. Now the input to this variable will be the ratio of perceived death rate to death rate threshold. And we need a lookup function, table function. And I believe it's going to be F7. Okay. So create an arrow like this. Okay, so you can see all the three effects coming from the death rate. They kind of look very similar. All right, now we're going to create the next variable. It's going to be called normal fraction of infected symptomatics quarantined. So it's the same idea as normal infectivity or normal contacts per day. So now we're going to calculate the adjusted fraction based on this pressure, right? So that variable is going to be fraction of infected symptomatics quarantined. And this is the response to the pressure. Okay, so we're going to make a note here. This is a response, policy response to the pressure to quarantine. All right. Now you're going to connect this effect of death rate on quarantine and normal fraction of infected symptomatics quarantined to this fraction of infected symptomatics quarantined. Unlike these infectivity or number of contacts per day, we need another variable here. The reasoning is if the death rate goes up, what that does is it's going to lower the infectivity and it's going to lower the number of contacts per day, right? However, if the death rate goes up, it's actually going to increase the fraction of people that's going to be quarantined. So the polarity is actually opposite from infectivity and number of contacts per day. And when you think about it, if the death rate goes really, really high, then we might get to a situation where these equations actually lead to the fraction of infected symptomatics quarantine to be over 100%, which is not realistic, right? So in such an extreme situation, we want to make sure this fraction does not exceed what's realistic. We're going to use another lookup function to address that issue, and we're going to call that F8. Okay. All right, now let's define the equations here. So first of all, let's go and plug in the numbers for F7. The type's gonna be lookup, okay? And then you can click as graph, and the coordinates on this graph is gonna be 0, okay, so these are the coordinates that we added to F7, okay? So we're gonna assume that if the perceived death rate is 20 times the death rate threshold, so a kind of 8 is showing how much pressure is being put on the fraction of infected symptomatics to be quarantined, okay? And if the death rate goes above the 20 times the death rate threshold, then it's going to continue to be at 8. Okay, so 8 is the most pressure that's going to be put on the fraction of infected symptomatics to be quarantined. Right, so that's what it means. Click OK. And now the unit's going to be dimensionless. All right, now the effective death rate on quarantine, that's gonna be F7, and then the input's gonna be ratio of perceived death rate to death rate threshold, and then again the unit's gonna be dimensionless. Click OK. Now the normal fraction of infected symptomatics to quarantine, symptomatics quarantined, we're gonna put that as 0.1. That is 10%. And then the unit's gonna be dimensionless. So the x-axis for F8 is gonna be, let's just define this first, open that up, okay? So it's gonna be F8, and then the input is gonna be normal fraction multiplied by the effective death rate on quarantine. So if you remember that, it ranges from 0.4 to 8, right? So that's the relative scale of the pressure that's coming. So that means that this normal fraction of infected symptomatics quarantine, since that's 0.1, okay, this x-axis, the input value, is gonna range from 0.04 to 0.8. Okay, so that's what the x value to this table function would be like. Okay, so you can set this to dimensionless. All right, so F8 is gonna be it's a lookup, and then the graph, the coordinates gonna be like this. Okay, it's really hard to see all these coordinates. So let's change the x maximum to 1, okay, and then y maximum to 1 as well. Now you can see the shape of this table function, right? So what's going on here is if the input x-axis is 1, then the maximum fraction of infected symptomatics quarantine that we're going to be getting is at 0.75. So this table function is assuming the maximum fraction that we can quarantine realistically is about 75% of those showing symptoms. Okay, and as we discussed before, the x-axis, right, is actually the normal fraction of infected symptomatics quarantined multiplied by the pressure coming from the death rate, right? And numerically, in the current setting, this x-axis ranges from 0.04 to 0.8. However, we can actually simulate the model with different value of normal fraction of infected symptomatics quarantined. So this value doesn't necessarily have to be set at 0.10. Or this effect, this table function here, F7, might also change so that the pressure coming from the death rate is actually greater than what we have defined. So in those cases, okay, we can still make sure that this fraction of infected symptomatics quarantine don't go above 1, okay, or actually don't go above 0.75 because of this table function that we defined with F8. Okay, so the F8 actually makes sure that our model runs even in the extreme situations of really high death rate or really high normal fraction of infected symptomatics quarantined, which would represent really strict policy measure. Okay, so you can click OK, and this is going to be dimensionless. All right. Now we have the fraction of infected symptomatics quarantined. Now we have to make sure that only those people who are not quarantined and who are not hospitalized are out in the community making contacts with susceptible people. Okay, so if you take a look at our current model, susceptible people make contact with infected asymptomatic population as well as infected symptomatic population. Okay, so since we're not gonna hospitalize or quarantine these asymptomatic people, things will be same in this case. However, now we're gonna get rid of this arrow coming from infected symptomatic population to the contacts. So we delete this. And what we're gonna do is we're gonna calculate those infected symptomatic population that are not quarantined and that are not hospitalized. Okay? So what we're gonna do is, first of all, create a variable. We're gonna call this variable infected symptomatics out of quarantine and out of hospital. Okay, so to calculate that, we need how many people we have, the infected symptomatics, okay, and then the fraction of infected symptomatics quarantined. So 1 minus this fraction would give us fraction of infected symptomatics not quarantined, okay, and we have to go back to this hospital sector. So we know the infected symptomatics that needs hospitalization. However, we need to compare that to the hospital availability, because only when there is a hospital beds available, these people needing hospitalization can actually go to the hospital, right? So what we're gonna do here is we're gonna add a variable, infected symptomatics in hospitalization. Okay, and that's gonna be determined by how many people need hospitalization and how much hospital beds that are available. Okay, so those are the two variables, and then we're gonna feed that into the infected symptomatics out of quarantine and hospitalization. Okay, and that will feed into the contacts between infected and susceptibles. All right, so let's define the equations. Infected symptomatics in hospitalization, it's gonna be how many people need hospitalization multiplied by hospital availability. So let's say that hospital availability is 50%, then only those people needing hospitalization, about 50% of them will be able to be hospitalized. Okay, so the unit's gonna be person. All right, so the infected, symptomatics out of quarantine and hospitalization, that is gonna be, first of all, the fraction of people who are not quarantined, that's gonna be, we open parenthesis, it's gonna be 1 minus fraction of infected, symptomatics, quarantined. Okay, and then we're gonna multiply that with, and then you can open the parenthesis, it's gonna be infected symptomatic population minus infected symptomatic in hospitalization. That's gonna be the equation, and then the unit's gonna be persons. Okay. Now the context between infected and susceptibles, now we need to modify that. So what we do here is we delete this infected symptomatic population from the equation. We just delete that. And in that place, we're gonna click this one, infected symptomatics out of quarantine and hospitalization. So we replace the overall infected symptomatics population with now those who are not hospitalized, who are not quarantined, and we should be good to go. Okay, let's save our model. Okay, now let's run the sim module 8 base. Okay, now we can also run module 8 base with burnout, which will be, turn on the burnout switch to 1. Okay, now let's check the results. Now let's see what happened to all our stocks. Okay, so susceptible. Now this is what's going on in module 8 base with burnout, without burnout. So as you see here, we don't see a huge change between these two simulation runs because we are talking about 80 million people as our overall population. And then, but with quarantine, now we have a greater number of susceptible population compared to module 7 when there was no quarantine. Let's see, infected symptomatic population looks like this. So now with the module 8 base with burnout, let me make it a little bit bigger. Okay. Now, and then with and without burnout, this is what module 8 looks like with quarantine. And then the green line, that's the without quarantine, just with hospitalization. So quarantine definitely helps in terms of lowering the number of infected people, but also slowing down the spread of the disease. In terms of the death rate, this is what it looks like. So with the quarantine policy, the death rate is lower than without one. If you look at the cumulative death, we end up with less death, right? So with burnout, we have slightly more cumulative death than without burnout. And with quarantine, we are doing much better in terms of cumulative death than module 7 where we didn't have any quarantine policy. Okay, now let's save the model. So in module 9, we're going to be adding fatigue to this model structure where as people are adjusting their behaviors to reduce the number of contacts per day or lower the infectivity, people kind of build fatigue and there is this pressure to go back to the behavioral mode prior to COVID. Thank you for joining the Module 8 model building today.